Let me start by telling you what people used to think. Back in Newton's time, the late 1600s, Newton said light is made of little particles, little corpuscles, flying through space. Makes sense, right? Light goes in straight lines, it bounces off mirrors the way you'd expect a ball to bounce off a wall. Particle picture works pretty well. But then there was this Dutch fellow, Huygens, and he said, no, light is a wave. And over the next couple hundred years, people did more and more experiments, and by the 1800s, everybody was pretty convinced Huygens was right. Light is definitely a wave. Why? Because of interference. Let me tell you about the most important experiment in all of this. It's called the double-slit experiment, and it was first done by a guy named Thomas Young in 1801. Here's what you do. You take a light source, you put it in front of a wall that has two narrow slits cut in it, and behind that, you put a screen to see where the light goes. Now, if light were just particles, little bullets flying through space, what would you expect to see on the screen? You'd see two bright strips, right? One behind each slit. The bullets go through one slit or the other and make a mark. But that's not what happens. Instead, you get this beautiful pattern of bright and dark bands all across the screen. Many bands, an interference pattern. And this, you see, is exactly what waves do. If you've ever thrown two stones into a pond at the same time, you've seen this. The ripples from each stone spread out, and where they meet, sometimes a peak meets a peak, and you get a bigger wave. Sometimes a peak meets a trough, and they cancel out. That's interference. So the light going through each slit spreads out like a wave, and these waves interfere with each other. Where they're in step, you get bright bands. Where they're out of step, they cancel, and you get darkness. Beautiful. Light is a wave. Case closed. Except no, not case closed at all, because then we come to 1905, and Einstein looks at something called the photoelectric effect. Now here's what happens in the photoelectric effect. You shine light on a metal surface, and electrons come flying out. Okay, that seems reasonable. The light wave gives energy to the electrons. But here's the weird part. If you make the light brighter, you don't get electrons with more energy. You just get more electrons. And if you use light with a lower frequency, below a certain threshold, you get no electrons at all, no matter how bright you make the light. This doesn't make any sense if light is a wave. A wave should just dump energy into the metal. And if you make it brighter, that's more energy. So the electrons should come out with more energy. But that's not what happens. Einstein explained it by saying light comes in little packets, little bundles of energy. We call them photons now. Each photon has an energy that depends on the frequency of the light. High frequency, high energy. Low frequency, low energy. And one photon kicks out one electron. If the photon doesn't have enough energy, the electron doesn't come out, period. Doesn't matter if you have a trillion low-energy photons, none of them can do the job alone. So light is particles after all, little packets of energy. But wait, we just said it makes interference patterns like a wave, so which is it? Now here's where it gets really interesting. Let's go back to that double-slit experiment, but let's make the light very dim. So dim that we're sending through one photon at a time, just one little particle of light. And we're going to watch very carefully where each one goes. What do you think happens? Well, we hear a click in our detector, and we see that the photon arrived at one particular spot. It didn't spread out all over the screen. It arrived at one definite place like a particle would. Good. Light is particles. But now we do this again and again and again, sending through one photon at a time, and we mark where each one lands. And after we've done this thousands of times, guess what pattern builds up? The interference pattern, the same bands of bright and dark regions. Now wait just a minute. How can one photon going through the apparatus all by itself interfere with anything? There's nothing else there to interfere with. This is the deep mystery. This one photon must somehow be going through both slits at the same time, interfering with itself, to produce this pattern. But when it arrives whole, at one place, like a particle. Okay, you're thinking, let me catch you at your game. I'll watch which slit the photon goes through. So we set up a little light to watch the slits, and sure enough, we can see the photon going through one slit or the other, never through both. Good. But now, when we look at the screen, the interference pattern is gone. We just get two strips, exactly what you'd expect from particles. The very act of looking at which slit the photon goes through changes what happens. This is not a problem with our equipment being clumsy or anything like that. This is fundamental. If you detect which path the photon takes, you get particle behavior. If you don't, you get wave behavior. It's as simple and as weird as that. Now I have to tell you that electrons do exactly the same thing. We think of electrons as particles, little bits of matter, and they are. But if you send them through a double slit, one at a time, they build up an interference pattern. Matter acts like waves, too. In fact, everything does this. We've done this experiment with big molecules, thousands of atoms. They all show this wave-particle behavior. The French physicist de Broglie figured out in 1924 that every particle has a wavelength associated with it. The wavelength depends on the momentum of the particle. For something big and heavy like a baseball, the wavelength is so incredibly tiny that you'd never notice any wave behavior. But for something small and light like an electron or a photon, the wavelength is big enough to matter. And you see interference in all the wave phenomena. So what is light really? Is it a wave or a particle? The honest answer is it's neither. It's something that we don't have a good everyday word for because we don't encounter this kind of thing in our everyday life. At different times, under different experimental conditions, it shows behavior that we recognize from our experience with waves or behavior that we recognize from our experience with particles. But it's its own thing, and it doesn't have to obey our expectations. You see, we're used to thinking of a wave as something smooth and spread out like water waves or sound waves, and we're used to thinking of a particle as something localized, something that's at one definite place at one definite time. But at the quantum scale, nature doesn't work the way our everyday intuition tells us it should. Here's the thing, and this is important. The mathematics we use to describe all this works perfectly. We can predict exactly what's going to happen in any experiment you want to do with light or electrons or anything else. The predictions are stunningly accurate. But the mathematics uses something called a probability amplitude, which is a kind of mathematical object that tells us the probability of finding the photon or electron at any particular place. This probability amplitude has some of the properties of waves. It can interfere with itself, it can diffract, it can do all the things waves do. But when you actually make a measurement, you find the particle at one definite location. The wave aspect tells you the probability of where you'll find it, but the finding itself is particle-like. This is quantum mechanics. And I have to tell you honestly, nobody understands quantum mechanics. What I mean is, we don't have a good picture in our heads. Using everyday objects and everyday experiences, that explains how this works. The reason is simple. Everyday objects don't behave this way. Quantum mechanics only becomes noticeable at very small scales. But even though we don't understand it in that deep, intuitive way, we can calculate with it. And the calculations agree with experiment to an absolutely remarkable degree. In quantum electrodynamics, which is the theory of how light and matter interact, we can calculate certain quantities to 10 decimal places and have them match the experimental measurements perfectly. It's the most accurate theory in all of science. So what should you take away from all this? First, light exhibits both wave-like and particle-like properties, depending on what experiment you do. This isn't because we're confused or our equipment isn't good enough. This is how nature actually works at the quantum level. Second, the double-slit experiment is at the heart of quantum mechanics. I've said that all of quantum mechanics can be gleaned from carefully thinking through the implications of this single experiment. If you can understand how one photon or one electron can go through both slits and interfere with itself, yet arrive at one definite spot when detected, you're grasping the essential weirdness of quantum mechanics. Third, observation matters. When you try to see which slit the photon goes through, you change the experiment. You get different results. This isn't mystical or philosophical. It's just a fact about how measurement works at the quantum scale. To see the photon, you have to bounce something off it, like another photon, and that interaction changes what happens. And fourth, the most important thing, don't let anyone tell you they truly understand why nature behaves this way. We have a mathematical framework that describes it perfectly, but the deep why of it, the reason nature chose to be this way rather than some other way, that we don't know, and that's okay. The fun in physics is figuring out what nature does, finding the patterns, making predictions, testing them, understanding why these are the rules rather than some other rules. Well, maybe that's a question for philosophers, or maybe it's a question we'll never be able to answer. But here's what I love about this. Light shows us that nature is far more interesting, far more subtle, far stranger than we could ever have imagined sitting in our armchairs just thinking about it. You have to go out and look at what nature is actually doing. And when you do, you find these marvelous surprises. The particle or wave question turns out to be the wrong question. It's like asking whether you're your mother's child or your father's child. You're both. Light isn't a wave that sometimes acts like particles, or particles that sometimes act like waves. It's its own thing, and we're lucky enough to be able to study it, measure it, and predict its behavior with incredible precision, even if we can't make a simple picture of it in our minds. And that, to me, is the wonderful thing about physics. Nature doesn't care what we think should be possible or impossible. Nature doesn't care if we find it intuitive or strange. Nature just is what it is. Our job is to figure out what that is as best we can with experiments and mathematics and careful thinking. And light, this wonderful phenomenon that lets us see everything around us, that travels from the stars to our eyes, that connects us to the entire universe. Light turns out to be one of the most beautiful and mysterious things we know about. The mystery of whether light is a particle or a wave led us to quantum mechanics, which is now the foundation for understanding chemistry, solid-state physics, how computer chips work, how lasers work, even how the sun produces its energy through nuclear fusion. All of this came from trying to understand this simple question about the nature of light. And we still can't picture it the way we picture a baseball or an ocean wave, but we understand it well enough to build the modern world on it. So the next time someone asks you whether light is a particle or a wave, you can smile and tell them it's both and neither. It's something more interesting than either. And if they want to really understand it, they should go and learn some quantum mechanics. It won't give them a simple picture, but it will give them the truth as best as we know it. And the truth is marvelous.